My name is Osama Yusuf. I'm a fifth year PhD candidate in computer engineering at the LLM lab at GW. The topic of my talk today is accelerating LLMs using in-memory computing. So just a quick overview of what you can expect in this talk. This work that I'm going to be presenting is going to revolve around the question, is an in-memory computing based accelerator for LLMs plausible? Just a quick rundown again of what to expect. I'll basically be talking about a hardware-software co-design approach that will utilize the concept of memristors and memristic neural networks. We'll have a few details of a software simulation framework developed, as well as an effort on the hardware prototype, which is basically going to be an end-to-end simulation framework accompanied by an actual hardware prototype. And then also at the end, highlight the need for additional fault tolerance in such accelerators. Starting off with the motivation, as we all know, large language models have taken the world by storm. A lot of their complexity over the past couple of years, a lot of their improvement benefits have arisen from the fact that they've grown exponentially in terms of their overall scale. And accompanying that is, of course, an exponential growth in the total energy consumption, or their power efficiency has also grown exponentially. So the question, the core motivation here is, can we come up with new energy efficient hardware solutions? And one candidate for that is something known as an in-memory computing accelerator. I'll talk about that briefly as well. But before I jump into that, I quickly want to highlight decoder-only large language models. So a large language model, there are many different flavors. You can have encoder models, or decoder-only models, or even encoder-decoder models. The core operation that ends up happening in one of these blocks is essentially a sequence of the attention operation as well as a feed-forward operation. The core operation within both of these chunks here is the vector matrix multiplication operation. Some of these matrix multiplications or vector matrix multiplications are going to be static, meaning you're going to know the exact matrices that are going to participate ahead of time, and some of these are going to be dynamic. So the key idea here that we'll expose when building or trying to build or identify an LLM accelerator for these systems based on memristors is that we'll try to accelerate these static matrix multiplication operations. And over here I have a quick rundown of GPT-3. The core idea here is that if you were to work out the actual vector matrix multiplication or the MAC operations that end up happening, 97% of these are essentially static operations. The reason why we're interested in dealing with these static operations is because they're much easier to deal with than trying to accelerate. And so I want to focus on these static operations. So let's quickly take a look at the overall complexity of the VMM or the vector matrix multiplication operation. In traditional architectures such as CPUs or GPUs, the best you could get is near quadratic effectively. The question we ask is, can we do any better? And the core idea here is that if we perform these computations in memory, we can of course improve this effective complexity by a lot. In the ideal scenario, you can perform this operation in constant time. So the catch here is in neuromorphic accelerators or neuromorphic architectures, your computations become noisy. And so as a result of that, realizing training or inference with these accelerators is not critical. And you have to come up with algorithmic solutions to solve these problems. So starting off now, we're trying to dive into what a memristor actually is. You can think of a memristor as simply being a resistor but with tunable conductance. You can perform certain operations such as either set the device's conductance, which essentially means to increase the device's conductance, or you can perform a reset operation, which goes the other way. If you arrange these individual devices in this crossfire architecture, what you can fundamentally realize at a circuit level is this vector matrix multiplication operation. And so the core idea now is we can map LLM weights to these memristic crossfires, and because of Ohm's law, we can actually perform this operation in constant time in the ideal scenario. So our vision here, as I mentioned, is a hardware-software co-design framework. We have an effort on actually creating an accurate, scalable framework for conducting software simulations and for understanding the specifications that would be required for such an accelerator. The second effort is towards the hardware side. And over here I have an actual picture of our setup. We have a 20,000 device chip. We have a custom PCB and a custom host board. And you can run high-level applications such as neural network inference via high-level Python applications. So it's a complete solution ranging from extreme low-level hardware to high-level software. So one thing I want to cover here is how do we actually go from these neural network weights to device conductances. Device conductances or resistances, they are physical quantities. You can't really have negative resistances. You can also not have zero resistances. Whereas when you talk about neural network weights, both of these conditions are possible. So the workaround here that we propose is to actually utilize an encoding scheme that's differential. What that means is each weight gets mapped to two devices, and the difference of those conductances is proportional to the original weight. And so what you can do is still realize this in parallel at the circuit level and still get your vector matrix multiplication outputs. And those outputs would still be proportional to the ideal output you would have gotten in software. So going on to the actual simulation framework that we built, there's two key steps here. The first is to actually inject non-idealities using an open source library for LLMs. We use the transformers library by Hugging Face. The second step is to actually just study the network performances at different levels of these noise sources. So overall, we go from weight matrices to conductances according to the encoding scheme, and then we have a bunch of operations or noise sources that we model in this simulation framework. I already talked about the encoding scheme. And next, I quickly want to talk about some of these other noise sources that we support in our model or in our simulation framework. You can have conductance variability, meaning two devices tuned to the exact same state may exhibit some differences. You can also have stuck at faults, meaning some devices may not be tunable at all. And when you realize it's at the system level, you will also have limitations in terms of the ADC and DAC quantization. So there is only a limited amount of precision you can support for your input voltages for output currents. The particular model I'll be presenting over the results for is going to be the ternary model, very similar to the example I showed in the encoding scheme slide. And we conduct benchmarks and gauge network performances over a wide variety of language model evaluation benchmarks. One of these is shown here as the physical interaction question answering dataset, or PICA for short. So the way we investigate this is we start by fixing all parameters of our simulation framework or all noise sources as ideal, and we start with conductance variability. On the x-axis, what we're doing is we're sweeping this conductance variability, and on the y-axis, we're gauging the network's performance as a function of these noise sources for conductance variability. What we do is that we find an acceptable level of degree of these noise sources that this language model can tolerate naturally, and this is indicated by this green region here. We want to be in this region because we want to still have our accelerator be such that it attains near software performance, which in this case is less than 1% or within 1% of our software baseline. The approach we take next is to stack other noise sources on top of this. That's exactly what's happening in the second plot right here. We're sweeping ADC or DAC quantization on top of the sweeping of conductance variability. And over here is just a joint plot showing, once you've injected all noise sources, you can also investigate them together and try to basically extract actual specifications for your LLM accelerator. And that's exactly what we do next. So we basically study and derive these specifications. This table, what it's indicating is what specifications will our devices and our system need to have in order to get near software performance on these LLM benchmarks. So once we have this, what we can do is now move to the hardware prototyping system. As soon as we do that, we realize that our hardware, our current generation hardware at least, there's two areas where it currently lags behind our ideal specifications. The first is the array sizes, but this is by design. Our current prototyping system isn't as big as it needs to be. But the second that's more concerning are these stuck at faults. So in order to solve this, we actually propose an algorithmic solution, but this is actually a device level issue, right? So what we do is we propose an algorithmic solution to it. We call this solution layered ensemble averaging. The idea here is instead of mapping each weight matrix in terms of conductances once to your memristic device crossbar, what you do is you map it multiple times to appropriate locations on the chip. Once you do this, what you can do is during inference time, instead of performing a single vector matrix multiplication operation, you can perform, in this case, you can perform it 3 times. And at the output, you can average your currents for each output dimension. And so that's exactly what's happening here. And there's different parameters that we propose here, but in essence, it's an averaging scheme where we average outputs for each layer in these memory systems. Next, what we did is we compared this algorithm that we proposed against state-of-the-art algorithms from literature. Our algorithm there in sample averaging is these red bars. The other two are the state-of-the-art algorithms we're comparing against. Regardless of the overall number of times you map each solution, what we found is that our solution performs much better, and this is by design compared to these other algorithms. We took this a step further and we actually demonstrated that this scheme works on an actual hardware implementation in tolerating these faults or stuck-at faults. What we did is we mapped these solutions for a much smaller network because of our hardware constraints. But it's a much smaller network, but the idea here that's being shown again is as we increase the redundancy, the performance of our non-ideal memristive implementation actually approaches the software baseline. And there's this diminishing returns. There's no benefit in going for mapping it even more redundantly beyond this beta equals 4 parameter. And another thing I want to highlight here is that this is technically the first hardware demonstration of any fault tolerance scheme when it comes to memristive neural network implementations. So I now want to just present a quick summary of my work. I started by talking about a hardware-software co-design approach for accelerating LLMs using in-memory computing. We built a very scalable software simulation framework that integrates with various open source libraries that models noise sources for memristive networks. What that allows us to do is derive ideal specifications, and we use those ideal specifications to gauge our current hardware. Then we realize that there is an issue in terms of fault tolerance that needs to be addressed, and so we propose a solution that effectively addresses it, and we demonstrate it both in simulation as well as this novel hardware prototype that we built. And with that, I thank everyone for listening, and I open the floor to questions.